Welcome back. This video is about bimolecular elimination reactions, also known as E2. Like any other reaction mechanism, that number at the end has absolutely nothing to do with the number of steps in the mechanism and everything to do with the number of reactants in the rate determining step, and therefore also the number of concentrations that show up in the rate law. This is a generic overall reaction, not yet the mechanism. But what we are going to see is a carbon-carbon single bond. And a carbon of interest, our alpha carbon, is going to be directly bonded to a leaving group. This carbon leaving group bond is going to be a polar covalent bond, with the leaving group being more electronegative. Another carbon is going to be bonded directly to this alpha carbon. Here I have one of them shown, and it's called a beta carbon, but it is possible to have more than one beta carbon. I didn't specify what is here, but if either of these start with a carbon, those would also be beta carbons. But what we care about is a hydrogen that is bonded directly to this beta carbon. There's going to be a base involved, and the products, you will see the leaving group and this beta hydrogen now attached to the base. Leaving group has left, and the two carbons now have a double bond between them. So each of these carbons lost a group, and the single bond went into a double bond. Let's look at a generic version of this reaction mechanism. So this reaction mechanism has only one step. That means we can call it a concerted reaction or a concerted mechanism. Our base has a lone pair of electrons on it. And that lone pair of electrons is going to attack our hydrogen that's on our beta carbon. So we need a curved arrow from that lone pair of electrons to this hydrogen. Two electrons are attacking, so the arrow gets two barbs. When that happens, a bond is going to start to form between the base and the hydrogen. Hydrogen does not like having two bonds, so at the same time, what's going to happen is that the electrons in this bond between the hydrogen and the carbon are going to move to between the two carbons. So again, we have a curved arrow with two barbs. This created another problem. Carbons can only have 4 bonds. Yes, so this bond is breaking and this bond is forming, but this carbon does not want 5 bonds. So when this happens, our electronegative leaving group is going to leave. So the 2 electrons in this bond are going to go to the leaving group. So another curved arrow with 2 bonds. So all at the same time, we have a bunch of bonds breaking and a bunch of bonds forming, and they're alternating. Forming, breaking, forming, breaking. Let's draw the transition state. Transition state might look just a little bit confusing. This is a dashed bond saying they're going away from you, whereas these are bonds forming or breaking. But this bond is forming, this bond is breaking, this bond is forming, this bond is breaking. All at the same time. This is going to have major implications later because it means that a lot of these orbitals need to line up in very specific geometries in order for this to work. But now let's draw our products. And here we go. We have a new carbon-carbon double bond. Whatever these 4 R groups are staying the same. Our base now has a proton attached to it, and our leaving group has left with the electrons in this bond, hence the negative charge. Let's switch to a real example. So this is showing the reaction of 2 bromopropane with hydroxide as our base. The reason that I'm doing this as our very first example is because this reactant has a certain symmetry about it such that all 6 of these hydrogens are equivalent. We can pick any of those 6 beta hydrogens and we only get one product. But first thing we do is identify the leaving group. So we need to find a polar covalent bond involving a carbon. So we have a carbon, bromine. This is our polar covalent bond, with bromine being the more electronegative. So bromine is our leaving group. That makes this carbon that the bromine is bonded to our alpha carbon. Immediately neighboring carbons are going to be beta carbons. And what we care about is a hydrogen on a beta carbon. And again, these are all 6 equivalent, so we can literally pick any of them. But we need lone pair of electrons from our base to attack one of these beta hydrogens. So curved arrow with 2 barbs. So this bond is going to start to form. And when that happens, the bond between that hydrogen and its carbon is going to break. And those 2 electrons are going to move to the carbon-carbon bond. So that's another curved arrow with 2 barbs. That puts this carbon in a precarious situation because we start to see a 5th bond forming, and it's not going to have that. So the easiest bond to break is the bond to this electronegative leaving group. So we have another curved arrow from those 2 electrons to the bromine, which is our leaving group. So let's draw our products. This carbon-carbon single bond is now a carbon-carbon double bond, and we have propene plus water because our base is now protonated, and our leaving group of bromide. If you need to identify the major and minor products when more than one product is formed, check out this video. Thanks for watching Chemistry in a Nutshell. If you feel that I've earned it, please like this video and subscribe to my channel.